In this video, I'm going to cover two basic layers of a graph neural network, the graph convolutional network, the GCN, and the graph attention network, GAT. Hopefully by the end of this video, you'll have a solid understanding of how these layers work. Some concepts you need to know before tackling GNNs are the basics of deep learning, an understanding of embeddings, and the basics of graphs. Without a proper understanding of these concepts, you'll have a hard time understanding the following slides. First, let's explore why graph neural networks are worth building in the first place. In other words, I want to motivate the need for something more than a dense neural network or a fully connected neural network to work with graph data. So say this is your graph, this is the adjacency matrix, and this is the feature vectors associated with your graph. One way to use a DNN on this is to concatenate the adjacency matrix and the feature vectors into a bigger matrix. You can then use a transpose of that as input to a DNN to make predictions for your task of interest, say node classification or link prediction. Now, this will probably do a fine job, but I want to note two major cons to this approach. First is that this DNN approach won't handle variable size graphs. So say if you add an extra node to this graph, this input matrix grows. As a result, it no longer matches what the DNN was trained on, so you'd have to retrain it, and that is just computationally expensive. Second, the DNN is sensitive to node ordering in the adjacency matrix. So say I switch this first and last column in this matrix. Although this doesn't change the meaning of the matrix, it'll look like a different input to the DNN, leading to different predictions. So for these reasons, we need a better way to use deep learning on graphs, thereby motivating GNNs. So GNNs, graph neural networks, are a broad class of neural networks designed to work on graph structured data. The key idea that I hope to get across on the next couple slides is that nodes in a graph have embeddings, and they update their embeddings or representations by aggregating information from their neighbors. There are many architectures that fall under GNNs, but for now we'll be talking about graph convolutional networks and graph attention networks. First off, what is a GNN doing? Say this is your input graph, and each node has its own input embeddings. For the sake of simplicity, I'm going to call the input node feature vector the input embeddings. Here, embeddings are represented by color, so all that a layer of a GNN is doing is transforming or updating the node embedding for every node from one layer to the next. So in this case, it's this layer of a GNN is updating this node embedding from blue to red. One thing I want to stress is that the structure of the graph, as you notice here, does not change when you pass it through a GNN layer. You can then use the node embeddings at this final layer for predictions such as node classification or link prediction. So this brings up the next question, right? How do you go about updating the node embeddings at every layer? If you think about it, one thing you could do is you could take your node of interest, say node A, look at its neighbors, B, D, and E, and somehow aggregate the information from these neighboring nodes, and then transform the aggregated embeddings, and that could be the new representation of your node. So this is what I'm trying to represent here. Aggregate the neighboring nodes of A, somehow transform it, and that could be the new node embedding for node A. Of course, you could also have node A as part of this aggregation down here, but you'll see that in the next few slides. Intuitively, this makes sense. One way to get updated node embeddings is to gather and transform the information from the node's neighbors. And there's a word for this, it's called message passing. No, we have not yet talked about the method for aggregating this information, but whatever that method is, it has to be flexible enough to account for a variable number of neighboring nodes. So in this example, for node A, it has 3 neighboring nodes, E has 2 neighboring nodes. So what is one way of doing what we just talked about? One thing you could do to aggregate the neighboring nodes is simply to take the element-wise average. of their embeddings. This is honestly a shockingly simple yet effective method of aggregation. Then, with this averaged embedding, you could transform it with a learnable weight matrix W, and add a nonlinearity, and that is now the new embedding for node A. So this is fairly simple, right? Oops. This is fairly simple. With that intuition, we can start formalizing it into an equation. So here, before we get on to describing this equation, H is the embedding of node V at layer L. NV is the set of neighbors of node V. This notation here is node degree, so basically the number of nodes. And finally, B and W are learnable matrices for layer L. These here are the model parameters. If you look at this equation, it's essentially describing what we talked about before. It's describing aggregation and transformation. So here we're saying for every neighbor of node V, we're going to sum them all up and normalize it by the node degree. This is just a fancy way of saying average. We then take the average and transform it with the weight matrix W. Here, since you're updating node V for the next layer, it's a good idea to use the embeddings at the previous layer of node V in this updating mechanism, and it's as simple as transforming with the learnable weight matrix W and just adding it to this component. Using two different weight matrices, W and B, will help make the model more robust, but as you'll see later, this is usually not how it's done in practice. This weight matrix W is usually shared between all the nodes. And finally, sigma here just represents some nonlinearity. And this is fairly straightforward, right? But unfortunately, you can't put this into a computer just yet because it's not an efficient form. So let's switch to a more efficient matrix-based formulation. Here, this isn't the full update rule just yet. For now, I want to show that this expression computes the mean of the neighbors of each node at layer L. In other words, this equation right here is similar to right here. Oops. And then just for notation, H of L denotes the matrix of node embeddings at layer L. So this is just one row is one node. Notice the transpose here. D is the degree matrix. So dii or dvv here equals to the degree of node V. Essentially, it's just a diagonal matrix, and each of the components of the diagonal is the number of neighbors that they have. Now, the inverse of D is essentially just 1 over the node degree. Now, if you perform this matrix multiplication, you will notice that this is essentially an efficient way of neighborhood averaging of every node. And I encourage you to try this out on your own and prove it to yourself. And now here, this is the complete efficient matrix-based formulation from the previous slide. First, we aggregate the messages with this notation right here, D inverse AH. Then a learnable weight matrix transforms the aggregated messages. And then we add this separate linear transformation of the current node embeddings. And after applying a nonlinearity, we obtain the updated embeddings for all nodes. So this is just the same update rule introduced earlier, but now written compactly in matrix form. Note this formulation naturally handles graphs of varying sizes because the parameters W and B are shared and do not grow with the number of nodes, so the model size stays constant. Again, I encourage you to pause and think about why this makes sense. Now, if you go to the paper that first introduced GCNs, right here, this is the feed-forward equation you will find. This is very similar to the one we just came up with, except for a few differences. A tilde here is the adjacency matrix plus the identity matrix. This introduces self-loops, so instead of having a separate weight matrix B, you can just reuse W. Also, the previous slide showed row normalization. Right here, D inverse. Right here is row normalization. The equation from the paper shows symmetric normalization. This just seems to work better in practice. And with that, congrats. You hopefully now understand graph convolutional networks. With this background, we can start talking about graph attention networks. Let me bring back this equation for neighborhood aggregation, this should be nothing new, right? I left out the second part of this equation with the B, learnable weight matrix B for demonstration purposes. But if you look at this equation, it's taking the node embeddings from a neighbor, right? Neighbor, scaling them by the node degree, and then adding them all up. Again, this is just a fancy way of saying it's the average, right? But I want to point out something here. By using this constant value, 1 over the node degree, you're essentially placing equal importance on each of the neighbors. So in this case, A, right? The node degree for A, this constant value 1 over 3 is placing an equal importance on node D, equal importance on node E, and equal importance on node B. In other words, this term here is forcing you to pay equal attention on all the nodes in your neighborhood. Now, this may not be optimal in practice because one node might be more important for this. In this case, like D might be more important to A than E is, and you can fix that issue by replacing that term with the learnable parameter A. Unfortunately, you can't just leave it like that. The problem with that is if you leave it like this, you're not placing constraints on A. So theoretically, the model could end up taking 100% of each of its neighbors. I hope you see the problem I'm trying to allude to here. There are no constraints to make sure that everything adds up to 1 in a sense. So if you go to the paper that introduces attention, right, this is what you'll see. So to calculate the attention parameter right here, this is the equation you'll find. One thing to note here is that this double sign means concatenate. And just to quickly describe this equation, the attention between node I and node J is found by transforming the node embeddings with learnable weight matrix W for node I and J, concatenate them together, and do the dot product with a learnable attention vector A. This vector is shared for every layer. And note that this would mean that since it's concatenated, A has to be twice the size of the node embedding dimension. Take a leaky ReLU of the dot product and normalize it with a softmax by going over its neighbors. And this calculates the attention that should be placed on each edge such that everything adds up to 1 in a sense. And with that, congrats. Hopefully you now have a good intuition of what graph convolutional networks are and graph attention networks. If you want to learn more, you can check out these papers. This one introduces GCNs, GATs, and this one introduced GCNs. You can also check out this CS224W Stanford course. It's a great course that'll help with a lot of this intuition. All right. Thank you for your attention, guys. Bye.